all gathered here to celebrate Phil Anderson's anniversary of his important paper, the 1958 paper. We are really honored to have him here at this workshop. And as every grad student quickly comes to realize, there is really no getting away from one of the many Anderson models. In fact, as we were putting the program together, it became abundantly clear that Phil Anderson's face and contributions were writ all over the program. For example, on day one, for those of you who were not part of the workshop, we discussed the superconductor insulator transition, and that basically began with Phil's 1959 paper on the pairing of exact eigenstates. In fact, next year we should all be back here to celebrate that paper. Now, today, the second day, we discussed the metal insulator transition, and that too began with his 1958 paper on absence of diffusion in random systems. And for this work, he got the Nobel Prize in 1977, which he shared with Van Vleck and Mott for their work on magnetism and disordered systems. And on day 3, tomorrow, we will see how yet another work of his, the 87 science paper, basically laid the foundation with his RVB theory for high temperature superconductivity. So basically, Phil Anderson is a singularity. He has dominated our field. He has given birth to many big ideas. And I think what has been really exciting about this workshop is seeing the evolution of these ideas over the years, paradigms made, paradigms broken, and the emergence of new directions. So with that, I'd like to ask Phil to share with us some of his thoughts.
Listening to Nandini, I had a faint tinge of regret. I've actually never invented a supermodel. So I'm one behind Sarkozy. It all started at Bell Labs, and you've all heard about the wonderful years at Bell Labs, but it didn't start out quite the way that one thinks of it nowadays. When I first went, it was already a pretty great place, and it had a lot of great people. And the reason I went was because it had John Bardeen and Charlie Cattell and Gregory Wanier and everyone else who was anyway, or at least they passed through everyone who was anyone in solid-state physics, which was being invented at that time. But one was expected to be a house theorist. Everyone was a house theorist for some group of experimentalists, and I was a house theorist for magnetic resonance because I'd done some stuff on line breadths and relaxation times, and so I was working away as the house theorist for that, and Conyers Herring was working away as a house theorist for semiconductors, or at least one semiconductor transport, and so on and so on. The trouble was that the Bell Labs at that time was leaking theorists. It had lost Bardeen, it had lost Cattell, it was about to lose Hal Lewis, it was about to lose Gregory Wanier, and they said, "Why are you leaking theorists?" And we said, because we feel dissed by being subordinate to the experimentalists, and so we want our own group. And wonder of wonders, they said yes, good, we'll do that. And so we got to Hal Lewis was a very, very good organizer. He later became chairman of Jason, and he invented the theory department at Bell Labs. Even though he was leaving, he did us the parting favor of inventing our theory department. And among other things, he said, "You need a summer program." And we started having this summer program for the years 56, 57, 58. And that's what I mean by everyone was there. We didn't confine ourselves to solid-state physicists. We had John Ward, we had Keith Bruckner, we had John G. Taylor, because my interactions with him led to some interesting stuff. But kind of solid-state physics was exploding under the influence of Wenzel came later on. That was very important for superconductivity. And I remember one afternoon when I was serving martinis simultaneously to John Ward and Keith Bruckner and Bob Schrieffer and Philippe Nozière and his wife and at that time, and about 30 other people. And it was an amazing time. One of the directions in which condensed matter theory was exploding at that time, hard to realize that we didn't really know how to do transport theory yet. And so there were at least three approaches to transport theory. There were two kind of heavy on the intellect and heavy on the reams of paper. One of them was the multiple scattering approach. We had Mel Lax. He came on board sometime during those years, and he had invented the multiple scattering approach during the war. Keith Bruckner was applying multiple scattering to nuclei, so there was a lot of work on multiple scattering, which I've described many times as the attempt to sweep the dirt under the rug rather than to think about the dirt and try to do something with it. We also had what, as I say here, was probably the last paper on transport in solids that really used classical Boltzmann theory. There were 50 pages by Kohn and Luttinger in two successive papers in PhysRev. And what really impressed me was that there were at least 10 appendices. I stopped counting it at 10. And yes, they did a lot. They did some very interesting things, including the anomalous Hall effect that Juan has just recently checked out. But they didn't find localization. And the least ambitious of these efforts was a little tiny effort that I was doing, and I didn't yet call it Cisport. That was a name by Larry Walker. It was the others were doing transport, but we were doing the opposite, so Larry Walker invented the name Cisport. And the motivation for that work came from that came from my years as a house theorist, because I'd gotten used to spending a lot of time in the laboratory of George Fayer. In those days, offices were not air-conditioned and laboratories were, and so I spent an especially large amount of time working with George Fayer. Let's see if this, no, it doesn't. Yeah, it did. George had this technique that he called Endor, because he was from Israel. He fought in the 48 war, and was familiar with the hill of Endor, which has a famous cave in which lived the witch of Endor. So he named his thing electron nuclear double resonance, and I'll show you some slides. I must remember to come back to this one, but first we'll run to a number. Oops. I'm sorry about these are copied from an old Reviews of Modern Physics paper, actually from my Nobel lecture, but the originals weren't very good either. So anyhow, the point is here and I think I have a laser pointer, that this was the system he was working on. There were phosphorus 31s. These were donors in a silicon lattice, and I've replaced the diamond lattice by a square lattice, and it doesn't matter. And this phosphorus 31 had an electron around it. It was a donor electron, and it's a well-known system. It has a big quasi-hydrogenic orbit, and but it has a big amplitude on the phosphorus, and so the phosphorus hyperfine interacts with the electronic spin rather strongly, but it also interacts with the 5% of silicon-29 nuclei. I've put in about 5% of extra spins. And these are in a random arrangement and pointing in random directions, and so they provide a random magnetic field that the electronic spins are in. Oops, still going wrong. This is the spectrum that you would see from these phosphorus 31s. If you have a low density, I think that's something like 10 to the 16th, you just see two hyperfine lines, one for each direction of the phosphorus spin relative to the external magnetic field. And there's a breadth, and the breadth of these lines can be shown to be almost entirely due to the atmosphere of silicon-29s, the random atmosphere that each one sees. Then when you increase the intensity, the number of phosphorus, you begin to see that the spectrum gets a little complicated, and you see this little hump in the middle, and you recognize that that's two phosphoruses close together exchanging their spins, and they're either in a triplet state or a singlet state, and the triplet state has three lines, the singlet state has the one line in the middle, and depending on how the phosphorus spin, I guess, yeah, anyhow, the basic point is there is a line for if the two phosphorus spins are opposite, or if the phosphorus spins are in a singlet state. But there's actually a little extra structure, and in this next spectrum, you can see the extra structure at one third and 2/3 of the way, and that means that there were three phosphoruses interacting. And so you can quantify the exchange interactions between the phosphoruses pretty well, and these could be calculated at the time. And in my little group doing CISPORT, it was Elihu Abrahams and David Pines, and Elihu was calculating these exchange integrals, and he said, yes, it's about the right level of interaction. This is the intensity at which they should be interacting, and at this concentrations, 4 times 10 to the 17th, they should be interacting quite strongly. And in fact, I won't talk about it, but it's significant that the lines have turned around. Then suddenly, somewhere around 3 times 10 to the 18th, there appeared a very sharp line, and this very sharp line is definitely a metallic line, definitely a resonance line of a metal, and the phosphoruses are running, the electrons from the phosphoruses are running all over the place, and are completely delocalized. Nobody had ever heard of localization, of course, at that time. So when I say delocalized, it has no significance. One of my main philosophical or technical, let's say, technical ways of thinking of how to do physics is that, in general, I've found that you get more new math out of looking hard at the experiments than you do out of contemplating your navel. And this is a very good example. The existing theory for this experiment was spin diffusion, which had been invented by Bloombergen for diffusion of nuclear spins in an atmosphere of lots of other nuclear spins. And Portis had done spin diffusion in electronic systems, and Bardeen and so on had invented the impurity band. And all of them were saying that if you had a hopping matrix element and a density of states, that the rate at which this transport process was bound to take place was the matrix element squared, the golden rule, the matrix element squared times the density of states. Now, our problem was, as we looked at George Fayer's work, oh, I guess I didn't give you the last slide, the final slide. I should have shown you. Wait a minute. Oh, this is the really messy slide. This shows what happens. What you can do with these lines is burn holes in them, because every line has a particular atmosphere of silicon 29s, and the silicon 29s aren't flipping very fast. You can burn a hole, and it will be a sharp, steep-sided line. But then if you apply a nuclear resonance frequency, a low frequency, you can move the silicon 29s, and you can identify every possible kind of silicon 29 that is interacting with the different, with the phosphoruses. Here's a big, no, this is a big dip. That is the silicon 29s that are far away from the phosphoruses. These are our specific silicon 29s. I'm sorry about the mess that George's way of presenting his data causes in on the modern screen. But anyhow, the basic point is you had many sharp lines, and each sharp line belonged to a particular silicon 29 at a particular distance from a particular phosphorus. And you could do this. You didn't have to do this in any hurry. You dug the hole in the line. You came back a second later, or even a minute later, and you could the silicon 29 would still have stayed still, not even flipped its spin, and so you could come in and flip its spin with an external signal. So nobody was moving. Absolutely nobody was diffusing. And we were kind of stuck. There was no way we could. So, to quote another friend of mine, Tom Lehrer, who wrote a song called Lobachevsky, and the younger people in the room won't ever have heard it. But what I'm going to do, plagiarize. Let no one else's work evade your eyes. Don't shade your eyes, but plagiarize. Only remember, please, always to call it research. So I set about plagiarizing, and first I learned diagrams. I didn't know diagrams. I was from Schwinger country, and Schwinger didn't use diagrams, but I had to use Feynman diagrams. The only thing, so I learned about them from Peter Wolf, who had read Dyson and Feynman and put me onto the appropriate papers. Another miracle was that Conyers Herring, who reads everything, had somehow read old copies of the Cambridge Philosophical Society magazine or something like that, in which an English mathematician named Hammersley was just inventing the process of percolation. So I had heard of critical probabilities and also about statistics of non-repeating paths. And that was thanks to Conyers. And I had to use sums on singular distributions, which I plagiarized from myself from my earlier line broadening work. And put all these things together and shook, and voila, proof that there exists a localized regime. Of course, what I was doing was not rigorous for any real system because there are always interactions, as we learned today. I was doing strictly linear, non-interacting quantum mechanical waves. But the great advantage of experiment, the great advantage of George Fayer's existing was I was sure it was true because I found a reason why George's Fayer might work, George's experiment might work, and otherwise it couldn't possibly have worked. So, I never had a moment's doubt. But whether it applied to such things as impurity bands and amorphous solids and all that, I didn't have any idea. Whoops, going back the wrong way. There was 20 years passed. The first 10 years, practically nothing happened except for Mott, except what was stimulated by Neville Mott, who became interested in this problem in about 1960. And he started out with this, idea of Yoffe and Regel, who said that transport theory was going to go crazy whenever the mean free path is less than the wavelength, because you can't understand a wave moving a distance less than its wavelength. Mott, already in 61, was suggesting that implied that there was something called a minimum metallic conductivity. E squared over h times kf to the minus 1, that's just the wavelength. The two-dimensional version of that, it turns out, had been already observed in 1914 by a man named W.F.G. Swan on a postdoc in Bristol. And the reason we know he was a postdoc in Bristol is that he called room temperature 290 degrees absolute. And he was working on bismuth films, so he was using the same system that somebody was talking about here. There is this quantum unit of resistivity, and in this work they first realized that or resistance that first involved, or conductance, that first realized that there was a unit which is sometimes called the von Klitzing, but I think there are about 4 other people who also deserve to have it named after them. And 2 of them are Landauer, who about this time realized that it was the conductance of a transmitting one-dimensional channel, and Thales, who realized that it might well be the critical conductance of a 2-dimensional metal. But all of these people were, for 10 years, were just producing, I guess there was one paper by Thales, that, with which I wrote with Thales, that further worked by the original methods. But gradually there came to be more and more interest in this question of metal insulator transitions, and finally there was this wonderful Les summer school in 1978, which was called the study of ill-condensed matter, and there's quite a famous book about that. And in 1979, all of a sudden there was even more stuff to do about localization. There was a gang of 4. We weren't the first people to think about scaling. Thales and also, who was it? Hiroki and Wegener had made some suggestions about scaling, but somehow ours was the one that caught on, and these are the personnel. Ramakrishnan was a visiting professor in Princeton. L.U. Abrahams was always in Princeton because he didn't like driving all the way to New Brunswick for his day job. Don Licciardello came from the team of Licciardello and Thales and kept reminding us, well, his presence reminded us of Thales's earlier work on scaling. And we had the idea of one parameter scaling of conductance in units of E squared over H versus size L. And the second idea, which Rama and L were responsible, that you could even calculate the first correction in 1 over G from using cross diagrams, and that idea came from an old paper by Langer, and that was the first appearance of weak localization, or not the first appearance, but that was much of the origin of weak localization. Somewhere back here, something got lost. I should have said that in the course of doing this work, the whole business of Endor and the problem actually got written up, and it got written up in a place that nobody, I think, ever reads it, but it should be obvious because it's that after the second paper on the Mott transition, there was David Pines happened to be there at the same meeting, and he gave a discussion remark, and he wrote up what we were doing very, very neatly and beautifully. So there is a Pines discussion remark in 1956, which is the first mention of the possibility of localization. Anyhow, let's go. There's one more experiment that I want to talk about. We still didn't really know that this weak localization was right, stuff was right. Jerry Dolan and Doug Osheroff were trying to verify Thales's ideas on one-dimensional wires, which were rather similar to some of the things we were talking about at this meeting, but and the things which have been done for many years, for a number of years since then. But Doug and Jerry realized, or Doug actually, can never take a straight line and really be sure that it's straight. He always sights along it to see if it's actually curved. And so he was the first person to realize that the resistivity of a two-dimensional film depends logarithmically on the temperature, which is the length over which the length is proportional to the length over which elastic scattering only elastic scattering takes place. So there are these final papers. The gang of three, Abrahams, Ramakrishnan, and myself, and Dolan and Osheroff was the first weak localization measurement. So after that, the floodgates were open. Thank you.